In this animation, we will take a look at what happens when hydrogen chloride gas is dissolved in water and how we can represent that when we're trying to write equations. So to begin with, we have all HCl, so we can assume that the gas is undissociated, unionized. And then as time goes on, we get more and more hydrogen ions that form and more chloride ions that form. And essentially, after a while, we have no HCl, and we have all hydrogen ions and all chloride ions. So if we pause for a second, we can take a look, and that represents the chloride ions, and that represents the hydrogen ions. Now, in reality, this reaction is taking place because water is there as the solvent, and the water is effectively pulling these hydrogen chloride molecules apart. So how can we represent that? So I'll show you two different ways. So the first way is we just say that we have hydrochloric acid in water, and the hydrogen ion, the proton, goes from the HCl to the H2O, so that gives us H3O plus, which is called the hydronium ion, and Cl minus. So in terms of the Bronsted-Lowry system, we would call this one the acid, and this one, the water, would be the base. This would be the conjugate acid, and this would be the conjugate base. And we draw a single arrow because we are assuming that this reaction goes to completion. Now, a lot of times we don't want to write the full equation. We write really sort of a shorthand version. So what does that look like? So in the shorthand version, which I'll do down here, we have HCl, and we just show that going to hydrogen and the chloride ion, and we leave water out. Water is understood to be there, but we don't actually write it in. So this one, the H plus, really stands for this one up here, which is the hydronium ion. So this one is this representation is a shorthand. All right, so now let's take a look and see what happens when we have a weak acid. Okay, so now we're going to take a look at hydrofluoric acid and what happens when we have this gas in water. So we'll play forward a little bit. So just like before, we have all HF to begin with, and after a time, a little bit of the hydrogen ion and the fluoride ion form. But what is different is we don't have nearly as much as we had before. So if we pause at this point and we take a look, we can see that most of the HF is in the undissociated form, and we have some ions, so there's one and there's another one there. So this is not really a quantitative representation. It's not really a simulation. It's more just an animation showing the basic ideas that we have. All right, so if we continue on here a little bit further, we get to a point where the relative numbers of HF compared to the H plus and the F minus will stay constant. All right, so how do we represent this? So because this is weak, I'm going to do it a little bit differently. So it's going to be HF and H2O. And here's what's different. The reaction doesn't go so far to the right, so I'm going to use a shorter arrow that direction and a longer arrow going back to the left. On this side, I'm still going to have a hydronium ion, and I'm going to have the fluoride ion. Okay, so again, we have the acid, the base, the conjugate acid, the conjugate base, and the simplified form of this one would be HF, short arrow, long arrow, H plus F minus. But again, it's weak because here we only have a small number of ions. So in the next video, we'll talk about what happens when a strong base is dissolved in water, and what we have with a weak base solution, and then we will go on and talk about what happens when we have combinations of acids and bases of various strengths.